Good afternoon and welcome to this afternoon's presentation, Role of Laboratory Testing in Geotechnical Engineering, presented by Brian Barnes, a professional engineer and senior engineer with Atlantic Testing Laboratories.
All right, thank you, Howard, and good afternoon, everyone. This afternoon, I'll be talking about the role of the Geotechnical Laboratory. And one of the challenges we face as geotechnical engineers is determining design soil parameters for a heterogeneous material such as soil, which can vary both vertically and horizontally below the surface, and sometimes in a very short distance across the project site. So we typically have to rely on experience and judgment from the information gathered during the field investigation, as well as the laboratory testing performed on representative soil samples taken across the project site. The geotechnical aspects are usually a small portion of the work that goes into a project, but can have significant cost and time impacts on the overall design and construction. One of the things we're often have to deal with is evaluating risks associated with different foundation types, such as shallow versus deep foundations, where spending a little more money in time during the design phase on higher level lab testing can lower the risk and have significant cost savings for the construction of the foundation system. So today's presentation is going to focus on some of the typical geotechnical laboratory tests that are performed on projects in our area in upstate New York. During the design phase of a project, the Geotech lab can help the engineer characterize the subsurface conditions for the project design. Other construction materials such as steel and concrete are typically produced in a factory setting with quality control performed during their fabrication. However, subsurface soils are highly variable, and depending on the mode of deposition by Mother Nature. So to help minimize those risks, lab testing is performed on representative samples in accordance with established test procedures, typically published procedures by the American Society of Testing Materials or ASTM for roadway projects. One of the main sources of error that sometimes occurs can be due to sample disturbance during the collection and testing. So it's important that proper procedures be followed from sample collection to completion of the lab testing. And per the building code in New York State, the laboratory testing program is determined by the registered design professional, which is typically the geotechnical engineer of record for the project. And the engineer is a person that knows the specifics of the project, so they're best suited to determine the number and location of samples, as well as the type of lab tests to perform and the conditions to perform those tests. It's also important that the laboratory and its staff be qualified to run the test specified. And the ASTM, American Society of Testing Materials, they outline the test procedures for each test. And ASTO and the U.S. Army Corps of Engineers, they have lab accreditation and validation programs to perform laboratory testing. Because we can't physically see all the subsurface conditions that exist below a project, we often rely on a combination of field observations as well as lab testing at select locations across the site, along with experience to evaluate the soil parameters that go into the geotechnical design. Some of the typical aspects we deal with are shallow and deep foundation systems. And when it comes to deep foundation systems, the subsurface conditions are usually very poor, and there may be several alternatives that can be evaluated. So engineers are often asked to evaluate the cost as well as the time constraints for each of those alternatives. Slabs and pavements, usually evaluating soils to shallow depths, typically in the 6 to 10 foot range. For retaining walls, evaluating the foundation soils, as well as the soils that will be retained by the wall. For slope stability, excavation stability, that's typically performed before, during, or sometimes after construction, or after there's an existing slope failure. And then finally, liquefaction analysis to determine the potential for the site soils to liquefy during a design earthquake event. And there's typically two approaches depending on the complexity and the risks associated with the project. The first approach is to correlate soil parameters to index tests, which can consist of a gradation, sometimes called the particle size analysis of the soil, as well as the Atterberg limits, which are used to classify the soil. Moisture content, unit weight. These index tests are relatively quick, low cost, but they do pose a little bit of higher risk from the geotechnical design standpoint. And engineers often rely on experience when correlating soil parameters using index tests. The second approach is to conduct performance tests to measure specific soil properties, such as shear strength, consolidation, hydraulic conductivity. These tests typically take some time to perform, so there's typically a higher cost associated with that. However, there can be a lower risk when designing based on the performance tests. And on some projects, it may make sense to use a combination of both approaches. So first, we need to get representative soil samples to the laboratory. And the representative samples should be determined by the engineer based on field observations of the varying soil conditions. Samples are sometimes collected by somebody other than the engineer or the actual lab personnel, so it's important to have good communication between all parties. It's also important to choose sampling methods that will preserve the sample quality, and I'll go into some of the different sampling methods shortly. Also need to make sure we have appropriate sample sizes. The test methods will typically dictate how much sample needs to be collected to run a specific test. So for example, a particle size analysis, the minimum sample size per that test method ranges from about 1 pound of material for 3/8 size material up to over 11 pounds for gravel particles up to 3 inches. And materials can't be reused between the different test methods, so something that needs to be considered is how many tests are going to be run during the testing phase. And it's not uncommon to sometimes have anywhere from 2 to 4 5-gallon bucket sizes of material shipped to the laboratory for testing. And we always want to make sure we minimize sample disturbance between the field and the laboratory. And then once the specimens are in the lab, I want to make sure that there's minimal disturbance during the testing of the materials. Some of the most common sampling methods consist of test pits, which are typically going to be dug by an excavator, as well as soil borings using a drill rig, where samples can be collected with a split spoon sampler or a Shelby Tube sampler. And the geotech engineer needs to determine the appropriate sample methods as well as the sampling intervals for the project. Test pits, as I mentioned, they're typically going to be dug with an excavator, and they're going to give a pretty good representation of the soils to shallow depths, as well as the groundwater conditions. And these are usually limited to about 8 to 12 foot in depth, depending on the size of the excavator. One of the downsides of these is they do disturb a very large area versus a soil boring. But you can see from the photo that the test pits actually give you a good representation of what the soil horizons are in the test pit. So you can see some changes there, changing coloration, as well as a change there. And it looks like the materials, as you go deeper, become a little bit more coarser in nature. So one of the things that we'll look at if we're looking at soil bearing capacity for a project at this elevation, typically the engineer is going to take a sample, a discrete sample from this location to evaluate that material. Whereas if we're looking at a material to be used as backfill for a foundation wall, it may make sense to sample the material here because once the material is excavated, it's all mixed together, and this is the material that's going to go back in as foundation wall backfill. The other good thing about test pits, as I mentioned, is we can get an idea of what the groundwater conditions are. If there's just a perch layer, what the seepage rates are, if there's going to be any special dewatering methods required if groundwater is encountered during a foundation excavation. The split spoon sampler. This is the mainstay in geotechnical engineering. Goes along with the soil borings. So the split spoon sampler, it's a 2 foot long sampler. It's got a 2-inch outside diameter. The inside diameter is 1 3/8 inches. So in coarse gravel materials, the amount of gravel particles is not going to be representative using the sampling method. So this sampler, it's driven into the ground at whatever depth is specified by the engineer. It's typically going to be, the boring is going to be advanced using hollow stem augers or some sort of casing down to the sampling depth. And then the split spoon sampler is lowered down into the hole, and it's driven 2 feet with a 140-pound hammer. Then once the sampler is extracted, the shoe comes off, and then the split spoon sampler splits into two halves so you can collect the sample. You can see here's a little basket that allows the sample to go up into the sampler and keeps the sample intact during extraction. Once the sample's taken out of the ground, it's typically classified by the engineer and put into jars or sample containers for transport back to the laboratory. And one of the things I mentioned, sample size might be a concern, especially if you have a gravel deposit that is being evaluated. This is a Shelby Tube sampler, and these are typically used to sample soft, cohesive soils, clays, clay silts, and these are pushed into the ground with a drill rig or excavation equipment. And these have a tapered cutting edge on them that allows the sample to go up into the sampler and minimizes the skin friction as it's being sampled. These are considered undisturbed samples. However, once you do remove soil from its natural state, there's always going to be some disturbance. Whereas the split spoon sampler, that's considered a disturbed sample because it's being driven into the ground with a hammer. And these are typically 2.5 to 3 inches in diameter. Once the samples are collected, Then the ends are typically waxed and capped for transport back to the laboratory. And it's important to make sure that the sample transport and laboratory prep procedures are followed. There is an ASTM for that. It's ASTM D4220. And I want to make sure the samples are sealed to prevent moisture loss, as well as color retention. Soil can change colors as it's being oxidized by air. As I mentioned, undisturbed samples, Shelby tubes, we want to take care with transporting those back to the laboratory. And it's important to make sure the samples are properly labeled and have the appropriate chain of custody documentation that goes along with the samples. There's always a certain amount of risk associated with geotechnical work. We don't have X-ray vision to see everything that's below the surface, so we're typically taking soil borings or samples at discrete locations. And I use this in a lot of my geotechnical presentations to emphasize the variability of subsurface conditions. So if we really needed to take one soil boring at a site and we happen to take it right at the spot, we would hit that big boulder there, and we may conclude that we have shallow rock at the site. So it's the sampling plan needs to be evaluated by the engineer, and it's always important to make sure we sample more than one location, if possible. And that brings us to question number 1.
Brian, you make it for me.
All right, question number 1, which sampling method is utilized to collect undisturbed soil samples? The answer is B, Shelby Tube. So to get into the index tests, these are the typical index tests, and you can see there's an associated ASTM testing procedure for each one. Sorry about that, I forgot to turn my ringer off. So the first one we'll talk about is particle size analysis. And the main purpose of the particle size analysis is to determine the percentage of the gravel, sand, silt, and clay in the soil, and as well as to classify the soil. And depending on if the soil is coarse grained or fine grained, that's going to dictate the methodology that the engineer will use to evaluate parameters such as shear strength and soil settlement in the laboratory. If the soils are mixed, then the engineer is going to need to determine which methodology is appropriate based on how they think the soil is going to behave. If it's going to behave as coarse-grained or fine-grained soil. And it can also be used to evaluate liquefaction potential, shear strength, bearing capacity, and permeability, which I'll talk about a little bit later on in the presentation. So the particle size analysis, there's typically 2 components to it. The first component, you can see here to the left, is a series of sieves. The soil sample with the appropriate size is ran through the series of sieves. down to a number 200 sieve, which has a square opening of 75 microns. Everything that's retained above the number 200 sieve is going to be sand and gravel. Everything that passes through the number 200 sieve is going to be silt and clay. And to determine the percentages of the silt and clay in the sample, there's another process called the hydrometer analysis, which you can see here to the right, where we're basically taking those particles, putting them into solution, and then measuring how those particles settle out versus time to come up with the percentages. So the first part, running the sample through the sieves, is pretty straightforward. Doesn't take a whole lot of time, whereas the hydrometer analysis, that takes a little bit more time to complete that part of it. But once that's done, that's going to tell us the percentages of each component in the soil sample. And the shape of the curve tells us a little bit about the soil type, as well as the properties of the soil. So curve A, that's the curve here that's got a gentle slope to it. That's considered a well-graded soil. So if you can envision a garbage bucket, which is filled with basketballs, volleyballs, softballs, golf balls, down to marble-sized particles. Basically, all the void spaces in there are taken up by the different particle sizes, which makes a well-graded material. And typically, the well-graded materials are going to have a high unit weight, higher shear strength, and then a lower permeability because more of the void spaces are taken up. And typically, New York State DOT Type 2 or Type 4 gravels for subbases for pavement and slabs are typically going to be considered well-graded. Curve B is a uniformly graded soil. Basically, it has about the same particle sizes. These are typically drainage materials, which have a lot of void spaces to them. And they're typically going to have a lower density, but a higher permeability because of the amount of voids. And typical materials that are uniformly graded are going to be like a DOT Type 2 or Type 1 stone product. Here's an example of a well-graded material, and you can see it's got a nice smooth curve based on the shape of it. And if you look down the different particles between the gravel, sand, silt, and clay, it's basically got just about equal components of each one. So this material has very little void space, high density, and when it's well compacted, is going to have typically a high shear strength. And here's just a photo of a typical well-graded material. This sample here probably doesn't have a lot of fines in it. It's mainly a sand and gravel with very little fines.
And quickly, there's a question.
Sure.
Isn't there a new ASTM standard for particle size analysis? That's a question. Is there a new standard?
There isn't a new standard as far as I know of, as far as the 422, but ASTM does typically update those periodically. So there may be a new version of the 422 out there. So to get into the moisture content, geotechnically speaking, excessive water is not a friend to soil. As the water content increases over the optimum moisture content, then the shear strength typically decreases and the compressibility typically increases, particularly for fine-grained soils. It's a very simple, very common test, and the general descriptions are dry, moist, wet, and saturated, whereas moist is typically where the material is at its optimal moisture content for compaction. As you get to the wet side, that's going to be wet of optimum, and the material is going to typically be become a little bit unstable once it gets on the wet side. And the material that's totally saturated is typically going to be below the groundwater table, where 100% of the void spaces are filled with water. And moisture content's important. If you have a site where there's going to be mass cuts and fills, it's important to know what the in situ moisture content is. That way, the contractor can have an idea if they're going to have to add water or if they're going to have to dry the material out as they're placing and compacting fill across the project site. It also gives an indication of where your groundwater table may be and if you have perched water layers, as well as aiding in evaluating construction dewatering and excavation stability, particularly to evaluate flow rates and filter materials. So the next test is the Atterberg Limits test. And the liquid limit, that's considered the moisture content where the soil changes from a plastic to a liquid state. The plastic limit is the moisture content where the soil changes from a semi-solid to a plastic. And then the plasticity index is just the difference between the two, which is the range of moisture contents where the soil is in a plastic state. And the Atterberg limits are typically performed on cohesive materials that you can roll with a thread, silts and clays. So the photo on the left is the liquid limit apparatus. And in this test, the sample is placed in the cup, and then there's a grooving tool that makes a groove in it. And the liquid limit is basically the moisture content where this gap closes up at 25 blows of that cup on the block there. Whereas the photo on the right, to determine the plastic limit, basically that's going to be the moisture content where the sample starts to crumble when it's being rolled to a thread of about 1/8 of an inch. So these are pretty quick, pretty simple tests to perform. And these are used to determine the soil classification and to estimate preliminary soil parameters, typically in conjunction with the moisture content for a degree of consolidation, to determine if the material is going to be under normally or over consolidated. There's also correlations for compressibility. The DOT Geotechnical Design Manual has a correlation for the compression index, which is used in settlement analysis, which is based on the liquid limit. And there's other correlations that go along with determining shear strength, shrink swell potential, as well as liquefaction potential for cohesive soil. And just a couple of photos to kind of show the difference. The photo on the left. So if you take a soil that's around its optimum moisture content is considered moist. If you ball it up in your hand and let it go, typically a non-cohesive soil is going to crumble in your hand, whereas a cohesive soil is typically going to keep its shape, as you can see there on the right. That brings us to question number 2.
Brian, please continue.
Okay, which type of lab tests provide a relatively quick, low-cost evaluation of various soil parameters? The answer is C, index tests. So moving on to the unit weight. This is used, the unit weight of soil is important to evaluate subsurface stresses, bearing capacity, as well as lateral loads on structures. And it's applicable to soils that will retain their shape. They do have to have some sort of cohesion to them. And it's basically measuring the weight per volume of the intact sample. And there are correlations for compressibility and shear strength based on the unit weight. Soil classification. Once we have the index test completed, the first step is determining what type of soil we're dealing with. And the most common classification system used in engineering applications is a unified system, which is the ASTM D2487. And there's basically two steps to it. The first step is determining the particle size analysis, determining if the soil is coarse grained or fine grained, and then determining the Atterberg limits of the fine grained materials. And this is one of the charts for the classification, for classifying the fines. The lower left soils, the CLs and the MLs are going to be the low plasticity based on the liquid limit and plasticity index, low plasticity clays and silts. Whereas to the right of this solid line, the MH and the CH are going to be the higher plasticity silts and clays. And the O's are going to be organic materials. Brings us to question 3.
Brian, please continue.
Question 3, which lab test is used to determine the percentages of sand and gravel in a sample? The answer is A, particle size analysis. So here's a typical table. This table is from the New York State Building Code. It's for the presumptive load-bearing values of various soil types. So you can see here on the left, once you have the material classified in accordance with the USCS classification, and you can come over and you can see what the recommended vertical foundation pressure is, lateral bearing pressure, as well as sliding resistance for those material types. The one thing with these tables is they don't take into account the density of the soil. And a lot of times some of these tables may be conservative, so it's always important to make sure that there is some additional lab testing done, or additional field testing, I should say, to verify the density of the material. Here's another chart from the DOT Geotech Design Manual, which correlates soil type in unit weight to the internal friction angle. So you can see here the unit weight once you have your soil type, and this does have density to it. So once you have your soil type, you know what the unit weight is, and you can come across and estimate what the internal friction angle of the soil is going to be. And this is going to be for a coarse grained soil. Your sands and gravels as well as non-plastic silts, VML materials. So to get into the performance tests, some of the performance tests I'm going to talk about are the shear strength tests, which are used to evaluate slope stability, bearing capacity, the consolidation test for settlement analysis, and the hydraulic conductivity test to evaluate the flow rate of water through soils. So from the shear strength test, we're looking to determine the undrained shear strength or cohesion and friction angle of a soil. So for coarse grained soils, we typically perform a direct shear test. There are a few more options for fine grained soils, which consist of unconfined compression test, the unconsolidated-undrained compression test, which is often called the UU test, or the consolidated-undrained compression test, which is often called the CU test. So it's up to the engineer to determine which test is appropriate based on the soil conditions and how they're going to evaluate the geotechnical issues on a project. And here's a photo of a direct shear machine. And this is actually one of the smaller machines. And in this test, the soil sample is placed into the two boxes. And then there's a normal load that's placed on the boxes, and then the boxes are sheared apart. And basically, 3 points are ran at different normal forces to determine the shear strength, and then from the data, the friction angle as well as the cohesion can be determined. And this test can be performed on Shelby Tube samples or remolded in the laboratory. So one of the things that the lab is going to require from the engineer that is specifying the test is going to be how to remold the sample, what percent compaction or density, as well as the moisture content, and then what normal forces to run the test at. The unconfined compression test. This determines the unconfined compressive strength. And from that, the undrained shear strength can be calculated. So basically, this has to be run on an intact sample that's going to retain its shape. And basically, it's loaded and then sheared without confinement. And once you have the compressive strength, then you can determine the undrained shear strength of the material. And this is a pretty quick and easy test to run. The unconsolidated undrained compression test, the UU test. Again, this is a relatively simple and quick. The sample is placed inside a rubber membrane, a flexible rubber membrane, and then it's placed inside another cell. And the outer chamber of the cell is filled with water to a specified confining pressure, and then the sample is immediately loaded to failure without the sample being able to consolidate. So the main purpose of this test is to determine the undrained shear strength for short-term loading situations where loads on a soil will happen relatively quickly, where the pore pressures are not able to dissipate. And these can be run on Shelby Tube samples. And again, the engineer needs to provide the criteria if it's going to be a remold, as well as the confining pressures to run the test. And here's a typical plot, the Mohr circle plots. This is out of the Geotechnical Design Manual. And from the Mohr circle plot, the undrained shear strength of the material can be determined. The third most common shear strength test, the Consolidated-Undrained test, or the CU test. Again, the sample is going to be placed in a flexible membrane, and then the chamber is going to be filled with water. And with this test, the sample is actually going to be allowed to consolidate. And once the sample is consolidated to whatever stress the engineer specifies, then the material is going to be sheared. This test here is going to take a little bit more time to complete because of the consolidation process. And this can be run on, again, Shelby tubes or remolded in the lab to determine the undrained shear strength. This will also determine the effective shear strength as well, because with this test, the pore pressures can be measured as the test is being performed. And here's a table out of the Geotechnical Design Manual, which has the maximum allowable undrained shear strength values for the different soil types. Per the design manual, these values should not be exceeded without laboratory testing and written permission from the Geotechnical Engineering Bureau. And the manual also has a table for the maximum allowable drain shear strengths. And again, these should not be exceeded without laboratory testing and written permission from the Geotech Engineering Bureau. The compressibility test, the mainstay for that is the one-dimensional consolidation test. And this is primarily used to evaluate the magnitude and rate of settlement of a saturated cohesive soil. And you can see here on the left, this is a 2.5 inch diameter by 3/4 inch high consolidometer ring. And the clay sample, which is typically going to be a Shelby tube sample, is placed in there. And then it's placed in the consolidometer. And then it's loaded so that the load versus deflection can be determined. And from that data, a consolidation curve is generated. Here's a curve from the Geotechnical Design Manual. And one of the important things that geotechnical engineers look at is the pass pressure of the clay. A lot of clays in New York State, because they've been glaciated, they've had a lot of weight over them due to the glaciers, or they've been dried out and desiccated. So they've had a much higher pressure on top of them than they currently see. So from a foundation design standpoint, if a foundation load is only going to be in this range on the consolidation curve, there's probably not going to be very much settlement of that foundation. However, on the other side of the pre-consolidation pressure, once you get over into this range, the clay is going to experience a lot more settlement. So that's what the purpose of this curve is to evaluate the settlement of clays due to new loading situations. And that brings us to question number 4.
Thank you, Brian.
Okay, question 4, shear strength test determine which soil parameter. It's going to be C, friction angle. So lastly, we're going to talk about hydraulic conductivity, and there's 2 methods that can typically be performed based on the soil type. The first is going to be a rigid wall test, which is typically performed on coarse grained soils that have a high permeability. The second is a flexible wall, typically performed on fine grained soils for low permeability soils, which are typically used for landfill caps or liners or earthen dams. So the rigid wall test, this is applicable to sands and gravels with less than 10% passing the number 200 sieve. And basically the material is, it's compacted or remolded into this rigid cell here. And basically water is run through it to determine the permeability rate of the soil. One of the things the lab needs from the engineer specifying the test is what percent compaction or density to run the test, as well as the initial moisture content to remold the specimen. The flexible wall test for fine grained soils. As I mentioned, this is typically performed for landfill projects or earthen dams where low permeability soil is required. And in this test, the sample is placed in a flexible membrane, and then the outer chamber is filled with water to a confining pressure. And then because these are clay soils that take a long time for water to run through them, in this test, water is actually forced through the sample to determine the permeability. And this test can be conducted on Shelby Tube samples as well as remolded samples. So the engineer is going to need to specify the remold criteria. The other thing, the engineer is going to need to specify the consolidation pressure as well as the hydraulic gradient to run the test. Because if the material is being evaluated for a landfill liner, it's going to have several feet of garbage over the top of it, which is going to induce a confining pressure. Whereas material for a landfill cap is going to have a lot less confining pressure and hydraulic gradient. So that's something the engineer is going to need to specify for that test. And here's some typical permeability ranges of natural soils. This is out of the Geotech Design Manual. So again, once you know your material classification, then you can estimate what the permeability of that soil is going to be. That brings us to question number 5.
Brian, please continue.
Okay, question 5. Which lab test is used to determine the permeability of a free draining gravel soil? And the answer is B, rigid wall. So to summarize, want to make sure we get representative quality samples from the field to the laboratory. And index tests provide a relatively quick, inexpensive means of estimating soil parameters such as friction angle, cohesion, and bearing capacity, liquefaction potential. Performance tests are used to determine the specific soil properties for final design recommendations. And the RDP, which is typically going to be the geotech engineer record, prescribes the laboratory testing and is going to evaluate the test results. So that concludes my presentation. I think we still have some more time for some questions if anybody has any.
Does the table in the building with presumptive bearing capacities include a factor of safety, or are these ultimate, or are those ultimate?
Yeah, those are considered presumptive allowable. So they do have a safety factor applied for shear failure.
If there are any other questions or comments, please share them now.
And if not, feel free to shoot me an email or give me a buzz to discuss any issues you might have.
Brian, there do not appear to be further questions.
Okay, well, I thank everyone for your time.
That concludes our presentation today. Please enjoy the rest of your day.